Thanks for that, Steve. Thanks for the opportunity to give you all this presentation today on the challenge of controlling registration in PCB manufacturing. A little bit about myself first. Dominic Millett. I've stepped in on behalf of Andy Kelly at the last minute. I work for Exact PCB as an application support manager. So who are Exact? A lot of you may not have heard of us. I know some of you have. I know there's a lot of familiar faces in the audience there. But basically, we're PCB veterans. We're a bunch of engineers who grew from what was interconnection systems, via system north and south, Tyneside and Circuitex. We're specialists in manufacturing and engineering, industry leaders with unrivaled expertise and the control and prediction of PCB registration. Misregistration in PCB manufacturing. It's a complex problem with multiple sources of distortion causing misregistration. The materials, the cores, the prepregs, the foils, the processes, lamination or bond, plating, brushing, any other mechanical processes. And of course the environment, we have temperature and humidity also are one of the sources of distortion. And of course the design, the copper layout, the construction, the stack. Why do you get material movement? Basically, PCB materials are composites. The prepreg and cores are generally manufactured from a woven E-glass. That's an electronic grade epoxy glass. And so we have both an inherent warp and in weft directions because the materials are made of effectively a cloth which is covered in the epoxy. The fundamental basic material of PCBs is the woven E-glass. As the E-glass is woven into the cloth, which is used for the laminate and prepreg manufacture, there's a difference in the tension in the warp and weft because it's a cloth which is forced into place and held, particularly on copper-clad laminate. Those tensions are held. Further stresses are induced as the material is manufactured from the long rolls of E-glass. So you have that stress in the warp direction and it remains under tension. I've got a section of slides now which take you through a typical manufacturing process. This process is, in the case of this example, it's a two-bond, two-stage manufacturing route. So you start with the copper-clad laminate, apply photoresist, apply an artwork, source of distortion in the artwork. You then have the next process. Stresses are relieved during the etch process as copper removed from that laminate which had the trapped tension which I mentioned earlier. You then have post-etch punch alignment, then the layer process, and then the bond process or the lamination process. So you have material movement during that process as well. You then continue manufacture with an X-ray or a vision system optimizer system to apply tooling holes and measure the panels. You then have the drill operation. Subsequent to the drill operation, you have chemical process. You apply copper in the barrel of the holes. During that process, you have moisture being absorbed in the barrel of those drilled holes. Again, sources of distortion. You may have mechanical processes. You may have a via fill process filling those holes, and then the panels get brushed again. So you have mechanical processes moving the panels again. And so it goes on. You apply an artwork. It's worth noting at this point that any scaling you've applied to the drill program may not actually now match the artwork that you're now going to lay on top of it because of the moisture uptake and any mechanical effects as well. So you have a slight mismatch between what was scaling on the drill and now scaling on the artwork. And so the process goes on. You have etch process again, more stress relief on those materials. Again, for the second stage bond, the layup, the lamination stage, the bond process, again, material movement through that process. Measurement, tooling holes applied, mechanical drill again, or maybe laser drill. Again, chemical processes in the barrel of the hole. Again, moisture absorption. Outer layer imaging, LDI, or maybe an artwork. So again, artwork's being used. And so it goes on. Electrical plate, and again, another etch process. So yet more stress relief on the final biscuit. Solder mask, exposure, artworks, Thermal effects now more stress relief on the finished biscuit. And then you have the metal finish, the legend, the depanelization. So all the way through the manufacturing process, there's several sources of distortion that artworks. Distortions occur during the generation of the artworks. Just how accurate is your plotter? How well controlled is the atmosphere, is the room that the artworks are actually generated in? Is it a temperature-controlled, humidity-controlled environment? Distortion occurs during the use of the artworks. Artworks show nonlinear distortion with changes in temperature and humidity. This could be transporting the artworks from the plot room to the print room, or up the street, as I've seen in some cases. Artworks are subject to mechanical distortion as well during use. I don't know how many of you have actually sat and maybe watched operators using artworks when they're actually physically printing panels. You'll be amazed just to what extent they push and pull artworks to fit on pins and just make the things fit sometimes. Typical values we've seen on distortion and artworks, and these are real world values that were measured during the research we've done in the past. Typically 50 microns error on an artwork, and this can be undersized, oversized, nonlinear distortion, rhombic distortion. Typically 50 microns, and that's on one artwork, and it's used several times in the process. Stress relief at etch. I've mentioned the tensions trapped in the material during the manufacturing process. As the removal of copper reduces the rigidity of the panels, those stresses are relieved. Typically, signal layers may only have 10% of copper left. So 90% of that stabilizing copper is being removed. Thin cores exhibit significantly more material movement, and material movement is non-linear. Typical values for a 0.1 millimeter core, 4 mil core, 150 micron shrinkage before and after the etch process. And that's only one etch operation. You may have 3, 4 or more etch operations in the production of a bowl. 150 micron shrinkage. Then you have the bond process, the material movement through the bond process, influenced by the various prepreg types, core thicknesses, resin types. Material supplier can be a significant influencing factor on the material movement through the bond process. Press cycle has an influence, and the copper distribution, the design of the panels themselves, can have an influence. Typically 50 to 600 microns over a 610 24-inch panel. And that's only for one bond cycle. If you have 2 bond cycles or more, that effect is there all of the time. Influences of prepregs. These slides illustrate the differences, the different types of prepregs can cause. Different glass styles have significantly different amounts of movement, and the warp and weft directions I spoke about earlier are significantly different again. The moisture uptake, the effects of the moisture uptake after a drill operation. When you drill panels, you put them through a chemical plating process. Typically, moisture is absorbed by the laminates during the electrolysis process. Areas around the drill holes absorb more moisture initially, and then as the materials are allowed to settle in production, that moisture is distributed throughout the panel, leading to up to 150 microns growth on a 24-inch panel. And again, you may have several plating operations, so that's happening again and again and again. All manufacturers suffer from these effects of distortion. We can't stop these effects. These effects are always going to happen. And as technology moves forward, as the products we're trying to make get more and more complex, this problem is just not going to go away. It's not going to get any easier. All that's going to happen is going to get more and more difficult. The impact on registration is driven by the technology of the products. Layer counts increasing. Materials changing, new products being issued to the market, and of course, from a lot of experience I have with designers, they want to use the latest material. They want to use the latest, fastest laminate. They want to get the fastest clock speeds. Feature size and density increasing. Increased build-up complexity, more layers going in. Typically, we've seen a lot of designs getting ever more complex, not necessarily driven by a circuit design, but driven by chip manufacturers. They've changed the chip package, and then suddenly, overnight, the chip's obsolete, Designers have to design to the latest, tightest BGA. Suddenly there's another 6 layers added to a construction. They need to add microvias and buried vias. And the thing is, their customer doesn't want to pay any more just because he's designed a more complex board. It's driven by chip manufacturers. Or, on the other side of the coin, technology is getting so much more complicated. Boards are getting so much tighter. More and more layers. More and more microvias. More and more buried vias. More and more sequential laminations. So the challenge of controlling registration, typically you may be looking at 150 micron annular ring. It's getting smaller. It's getting to 100 microns as technology moves forward. Design requirements are getting tougher. But material variation is still the same. 150 microns may be your capability. Throw in the process variation, again 150 microns. But the designs you're trying to make are 100 microns. Requirement versus capability. Getting tougher. It's not getting any easier, as I say. You have new materials coming on the market. No production history. What do? How is it going to perform? How is it going to move? Product density increasing. Less registration tolerance per process to play with. Sequential build, more processes to register to. More layers going in. More bond cycles. It's getting tougher. And of course, everything's quick turn, low volume. There's no opportunity for pilot lots. There's no opportunity for a remake. Product's got to be right by the first time. And the thing is, if you can't make it, somebody else will. So the challenge is the front end guys, the cam guys are trying to generate tooling, trying to generate artworks and drill tapes for an annular ring which is only getting smaller. The target they're trying to hit is getting tougher and tougher to hit. The production guy, oh, you've missed again, we've got misregistration, we've got scrap. Things are getting tougher, it's getting harder. LDI and laser drill, is that not the answer? You can align and compensate and scale. That's good, isn't it? Well, it depends what you're aligning to. If the inner layers are nominal, if you're getting scaling right on the inner layers, fine. The microvias can hit the inner layer pads, great. Through via, hit the inner layer pads, great, no problem. Everything's okay when your starting scale layers are correct. What if there's a uniform scale error on the inner layers? Okay, I've got laser drill. I can scale my laser drill to hit those inner layer pads. I can scale my through drill to hit those inner layer pads. I can scale my outer layer artworks on my LDI machine to hit all of those holes. Great. Get the inner layer scaling wrong, you end up with a board the wrong size. All the processes will follow that error and you'll end up with a board that's the wrong size. The customer will have to deal with the problem. And I've heard of this time and time again where stencil screens just don't fit the boards. I've heard of cases where a particular board needed 3 stencil screens just to get the board assembled. All because the board manufacturer did a little bit of scaling, a little bit of fixing, and I thought they delivered a product on time, and all it did was cause the assembler a real headache. What if you have differing scale levels, scale outs on inner layers? In the case of this construction, it's a 6-layer board, 2 cores, a different scale error on each core. Okay, you can scale the microvias on one side, hit the inner layer pads, scale the microvias on the other side, hit the inner layer pads, but then the through drill doesn't hit anything. Not only do you end up with a board that's the wrong size, you end up with a board that's potentially scrap. The best LDI and laser drill can't correct or realign the misregistered inner layers. And take that a step further to an even more complex build-up. And this isn't a construction we invented. This isn't a build we thought, let's go and do a pretty picture, which is pretty tough. This is a real-world construction. The challenge is getting even greater. So what's the answer? Exact has an approach where we take data. We take measurement data, we take stack-up information, and we turn that data into knowledge. The Exact system is a simple-to-use solution for the industry's most complex problem. The heart of the system, the key feature, is this predictive intelligence. What the system does, it takes all of these external factors we've just discussed, the effects of materials, the effects of processes, uses all of those to give predicted scale factors, i.e. get those inner layer scale factors right at the beginning and everything else follows. The registration is going to be good. Get the inner scale factors bang on, processing is going to be good. High yields. The system predicts artwork scaling, which removes the need for internal prototyping. There's a stack-up module which allows configurable materials. Any materials can be added into this stack-up module, and the system gives you predicted scale factors. The stack-up module predicts and simulates material movement in that any material. Give you a very brief outline of the system, the idea of what it is. You have the stack-up. The system gives you predicted scale factors. These are your artwork scale factors you apply in production. And then after the bond cycle, you measure the panels. That measurement data, those coordinate measurements, are then matched with the stack of information fed into a database. This is a screenshot of the measurements of the particular panels you just measured on your X-ray or vision system. These are the four corners of the panel showing worst case registration errors. The system also generates an optimized drill program to give you a best fit for all of the inner layer parts. And so the product continues in manufacture. As I say, we have the measurements matched to that particular construction stored into a database. And so you go around for the next build. You have the bill of materials, process information, measurement data stored in the database. You have another stack up. Again, system gives you predicted scale factors. You go around through the production cycle, measure panels, that information is matched together, stack up measurements into the database. Predictive engine works on all of that information to give you trends, to give you statistical analysis in order to produce predicted scale factors for the inner outputs. And so the more measurements are taken, the more various and differing constructions are fed into the system, the more it learns and the faster it learns. The system has the capability to interrogate that database to give you material movement over time. You can analyze and filter that data by part numbers, by dates, by layer counts, by materials, by core thickness, by supplier. All of that information, which you've just been storing in the database over time, can be interrogated to spot trends, spot equipment going out of tolerance, spot processing problems. The system's capable of giving you, as you can see there, 3D virtual cross-section at the point of measurement. This is before drill. You haven't made this product. You haven't sectioned this product. You've bonded it, you've measured it. That's what the registration looks like for that particular panel, and that's real. That's real measurement thrown up on a 3D screen, and you can zoom in on that. You can analyze one corner of the panel. You can see that actual panel in a cross-sectional view without actually doing a section. It's a non-destructive process, and it's instantaneous. You've just measured that panel, and that's what the registration looks like. You can filter those results to show an IPC, class 2 or class 3, pass or fail. You can change the angle of sectioning to get the best fit, or indeed the worst fit. And so I'll leave you with this parting word, parting phrase: embrace new technologies to survive. Okay? Thank you.